Hi everyone, in this video I'm going to be talking about gradient in two-dimension function. Now in my other video I discussed about gradient in one dimension, but in real life, uh, when we work on model, we work on function that has higher dimension than one dimension. For example, you can have a surface with x and y coordinate right there. That's two dimension right there. And when you work in one dimension, there might be some challenges. For example, when we find um, a local minimum or something like that, it might not turn out to be a minimum at all. It just happened to be the slope to be zero. But in higher dimension, that problem might be less prevalent than in one dimension. And of course, we also have in either dimension, we also have methodology to correct and to overcome those challenges right there. If you take a look, for example, right here in this Google Colab, and you can see that first of all, I'm going to import NumPy, math.lib, the random library, and SymPy right here. The math.lib is to plot the function. The NumPy is to generate the data point, and a random is also, for example, when we start our initial starting point to descend, then we could want to use a random starting point. And SymPy is to do algebra to make the equation symbolically. Okay. Now, another thing you also want to I also put here is that here is the symbol for the partial derivative. Here is the gradient. The partial derivative is, for example, if you have a graph like a function like this right here. What it means is that if you take the partial derivative with respect to x, that means that you keep everything else constant, or you keep y constant, and you just take normal derivative like this right here. And the gradient is just the partial of all of the variables. So if you have two variables, x and y, then you do a partial derivative of x and partial derivative of y. So this is the gradient right here. And I make this function using latex, and for Colab, we just use the text cell. We create text cell. We put the question mark right here, and then we do the symbol within the question mark right here. So for example, this one right here is the partial derivative with respect to x. Okay. And for example, in this first example right here, right, we just gonna plot this function right here, which is x squared minus y squared, and from the space -2 to 2 x and y right here, and we're gonna do a 3D plot right here. You can see right here, right, and you notice that, for example, at this point right here, right, both of the derivative, partial derivative, give us kind of a zero slope right here, for example. But in in higher dimension right here, right, this wouldn't consider the minimum, for example. So some of the challenges that we encounter in one dimension, it might not be so in two dimension. And I also mentioned that there's other technique that can resolve these challenges if we run into them. And if you take a look at this graph right here, right? This graph right here, this plot right, 3D plot right here is of the function x squared minus y squared. It's pretty simple. The minimum is going to be 0, 0, and everything else is going to be bigger than the minimum right there, right? So we can see that the minimum should be 0, 0, and any gradient descent should go to this point right here. Okay. Now to do the gradient descent, we can define the function, and this is how you define a function in Python, def with a colon. And this function taking two values, x and y, is going to return x squared plus y squared right here. And then for the partial derivative, you notice that it's more or less the same with both of x and y. So the partial derivative with respect to x is 2 times 2 times x to the 1 power right here. Right. So for this, I'm just using one definition, one function definition for both partial derivative of x and y. Just put in the point, return 2 times points right here, partial derivative. Now to do the gradient descent, right? We're gonna specify the learning rate and the epoch. Epoch is just basically the number of iteration it's gonna go, and the learning rate is gonna scaling the step, each step that is how wide, how small of the step is taken right here. So in this example, I'm setting the epoch to be 1000 and the learning rate is 0.01. So I'm gonna start at this point right here. I'm gonna start two random. I'm gonna start a random starting point using the random function, uniform function of the random library, and it's basically gonna pick a random point between -2 and 2, put in the x direction, put another random point between -2 and 2, and put in the y position. And so here is the temp right here, and so this one right here is just a starting point, okay. And then I'm gonna go through the algorithm in this for loop right here, basically from 0 to 1000, and the gradient is basically just the partial derivative, okay. This one right here is x, 0, your starting point is 0 for Python, and 1 is the second part y. So gradient is partial derivative with respect to x, and then this right here partial derivative with respect to y. So when we found the gradient, we updating our position, and in the algorithm, basically minus is going the opposite of the slope. If the slope point positive, you're gonna go minus. If the slope is minus, you're gonna point positive right here. So this one right here is updating the x position, the 0, and this one right here is updating the second position right here. And then it's gonna print out the final position. Now this one right here is a simple example, right? So wherever you start, it's gonna drive eventually to the point 0, 0 right here, okay? So let me run it again. See right there, right? This is practically 0, this is practically 0. So anywhere, this minus 1.8 and 0.8 is 0, 0, and there's also 0, 0, 0, 0 right here. So for a more challenging example, we can take a look at this equation right here, x times e exponential exponent to the minus x squared minus y squared right here. And here is a plot of this equation using the range from -2 to 2 at every 0.1 increment right here, right? And by the way, you can notice that I have to convert x and y into the mask grid right here, right? And the mask grid is basically the mask grid function is used to create a rectangular grid out of two given one-dimensional array right there, and it's necessary to plot to plot in 3D right here. Okay, so noticing that this function right here, right, you can see that it has a minimum of somewhere where x, this is x, where x is going to be about 0.707 and y is going to be equal to 0 right here. Okay, and we can look at this, we can compute this using SymPy. So I could create both symbols x and y right here. Okay, and then I can create a function z using the symbol right here, and then here is the exponent x squared minus y squared minus x times this whole thing right here. In order to do the calculation, we have to do the lambdify, use the lambdify function right here to lambdify partial the derivative of x, partial derivative of y, and here is an example of the calculation. Print out the function right here, partial x, partial y at this point right here. And you notice also, for example, right, if you do the partial derivative of x, partial derivative of y, here are the results of that. And you notice that, for example, there's a product rule. So if you're going to do the derivative with respect to x, for example, right here, right, you have this time the derivative of this, which is 2 times x to the 1 right here, right? And if you bring out like this, it would be minus 2x squared right here. And then it would be, the next one would be this time the derivative of this, which is 1, which is this one right here, okay? And then the derivative for with respect to y is pretty simple. It's just going to be 2y right here, okay? And multiply by the whole expression right here. And then as I mentioned earlier, you can do the calculation. You can put in the number and do the calculation right here, okay? And you can use the solve function right here to solve for the stationary point with respect to partial derivative of x and partial derivative of y. So yeah, you can see right here, right, when I print it out, the point is that when x is equal to square root of 2 over 2, either plus or minus, then this one right here is going to be the opposite of this expression right here, so this will be 0. And then for the partial derivative of y, right, either x0 or y0 would give you the 0 slope right there, okay? So for the training, for example, right here, right, it's going to be a little bit more I would say a bit more complicated than the one-dimensional array, one-dimensional gradient. But the concept, the conceptual step is just the same. For example, right here, right, we start a point at this guy and this guy right here. We pick a random point between minus 2 and 2, give it to x, minus 2 and 2, give it to y. And then over here, right, we calculate the gradient with respect to x right here. And this one right here is a gradient with respect to y, right? We store that value in the gradient variable. And then we update our initial position using the learning rate and the gradient right here with the minus sign. And then we print out, at the end, we print out the final step right here. So if you have a starting point somewhere in here, it's going to drive you here. But if you have a starting point somewhere in here, it's not going to be able to find the minimum right there. So that's one thing about gradient descent, is that in a way, it kind of depends on your starting point. So if I run the example again right here, right, you notice that if I started on the minus side, x on the minus side, I'll be able to find the approximation close enough to 0 and to square root of 2 over 2. But if I started on the other side, you notice that it does not give us that the correct result. So here's an example of gradient descent in 2 dimensions. I hope that you find it helpful and educational. If you do, please give a like, give a heart, give a thumb up, a comment. Thank you and have a good day.